You are driving along the road at 30 meters per second when you notice a deer in the road 40 meters in front of you. You immediately slam on the brakes and experience an acceleration of negative 10 meters per second squared. This is a kinematics problem, and so the method by which we'll solve it is to ask ourselves a series of well-formed questions. Now, one of the complexities in this problem is that there are two objects that we need to deal with. One is the motion of the car, and the other is the motion of the deer. Whenever you have two objects in one problem, the most important thing that you can do is be very careful with your notation. Never use the variable x or v or a, because that doesn't specify which object you're talking about. Instead, always use x with a subscript, let's say C for the car and D for the deer, V with a subscript, and A with a subscript. So let's begin. The first thing I'd like to do is collect the information from the problem itself. The first number we see in the problem is the 30 meters per second. And if we think about it for a moment, that is a velocity. It's a velocity of the car, but it is the initial velocity before you hit the brakes. So this says that V0 of the car is equal to 30. The next number in the problem is the location of the deer. This is 40 meters in front of you. Be careful not to use this location as the location of the car, because you're not there. This is the initial x location of the deer, and we'll change colors and write that as x0 of the deer is equal to 40. Finally, you slam on the brakes and experience an acceleration of minus 10 meters per second squared. That applies to the car and not the deer, so acceleration of the car is equal to minus 10. All of these are well-formed expressions because each one of these, an x0, a v0, or an acceleration, all of them are constants. And so we don't have to extract a double condition such as x at a particular time or v at a particular time. Let's go to the first question. Where would you come to a stop if the deer were not in your way? Well, where is a question that is answered by specifying a value for x. However, we need to be careful. X of the deer, x of the car. This is where would you come to a stop. So that's asking, what is the x of the car? Currently, that's an ill-formed question because in the beginning, the x of the car is 0. Then it's 10 meters, then it's 20 meters. Maybe it gets to 30, maybe it gets to 40. We don't know yet. Asking what is the value of x of the car is an ill-formed question since x is a variable. We need to instead specify the x of the car under a particular condition. And the condition is, where would you come to a stop? Stop means that the velocity of the car is equal to 0. Now that we've formulated this expression, we can see that the question asks for a position under a condition on velocity, and so therefore it uses the velocity position condition to solve. This is the third equation, quote unquote, and to make sure that we write it well, we need to be careful with our subscripts to say that the velocity of the car squared is equal to the initial velocity of the car squared plus twice the acceleration of the car times the x of the car minus x0 of the car. All we'll need to do is plug in velocity of the car equals 0 into this expression, move the variables around a little bit, and we expect that the only unknown is going to be the x location at which the car stops. This gives us 0 squared is 30 squared. Twice negative 10 is minus 20 times the quantity x of the car, which is what we're looking for, minus the initial position of the car. If at this point you had not been careful with your notation, you might be tempted to put 40 in there, but that's not where the car begins, that's where the deer begins. The car begins at location 0. So we can solve this out. X of the car will be 30 squared, which is 900, divided by 20, which is the same as 90 over 2, which is 45 meters. Bad news, that's a longer distance than the deer, and so it seems like you're probably going to hit the poor deer. How fast are you going when you reach the deer's position? So how fast asks for the variable velocity. This is not only an ill-formed question as written so far, but it's not even explicit about which velocity we care about. We want to know the velocity of the car, but the velocity of the car begins at 30, drops to 20, drops to 10, eventually reaches 0, and so this does not give us the answer that we want to know. We would like to know the velocity of the car under a particular condition, and that condition is when you reach the deer's location. So that's asking that the moment in question is that when the x of the car is equal to the 40, which is the deer's location. Let's answer this. Again, it's a relationship between velocity and position. So how we solve it is using the equation velocity of the car squared equals velocity 0 of the car squared plus twice the acceleration of the car times x of the car minus x0 of the car. Substituting in x of the car equals 40, we'll be able to find this velocity. So velocity car squared will be equal to 30 squared. Twice the acceleration is minus 20, and x minus x0 is an x of 40 as requested in our own question, minus the x0 of the car, which is 0. This gives us velocity of the car squared is 900 minus 2 times 4 is 8 with 2 zeros, 800, which is 100, so that the velocity of the car at this point is the square root of 100, and so it's 10 meter per second. Part C asks us, how long did it take you to get there? So how long is answered by specifying a value for the variable t. Notice that I don't have to specify whether I'm talking about t for the car or t for the deer, because both of these two objects experience the same time. However, as formulated so far, the question simply says when. We need to specify when what. And the question is, how long does it take you, you're the car, to get there? So that says x of the car should be equal to 40, because following part B, we're talking about the location where the deer is found. This is not the only way to formulate this question. We know another piece of information about when you reach the location of the deer. We solved in part B to find that at the location of the deer, the velocity of the car is 10 meter per second. Either one of these two questions will lead us to an equation. Both equations will yield the same result so long as we haven't made any mistakes so far. I'm going to recommend that we go with the first of these two, and the reason is this question uses only that information that was originally given in the problem. The second formulation of the equation with velocity of the car equals 10 relies on a result we calculated, and although I'm fairly confident in what we calculated, I don't want to take the risk, and so we're simply going to solve it the first way. The car's position as a function of time is given by x car is x0 of the car plus v0 of the car, notation, 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 times time, plus 1/2 acceleration of the car times time squared. Our job is to plug in 40 for the x location of the car and solve it for t. The initial location of the car is 0. The initial velocity of the car is 30 meters per second, and half of the negative 10 meter per second squared is negative 5. We can do two things to simplify this equation. Number one, we can pull all of the variables to the left, and number two, we can divide out the 5 because all of the numbers in this problem are rather simple. This will leave us with t squared minus 30 over 5 is 6t plus 40 over 5 is 8. Because the numbers in this problem are so round, this can be easily factorized into t minus 2 times t minus 4 is equal to 0. When you find that a product of two things is equal to 0, it means that either the first one is 0, meaning t would be 2, or the second one is 0, meaning t would be 4. Let's stop for a moment and imagine what this means. According to our mathematics, there are two moments in time when you pass the location of the deer. How does that make sense? When you stop a car, you will experience a negative acceleration until the car reaches 0 velocity, and then you will maintain 0 velocity having come to a stop and sit at one spot. You would only cross the location of the deer once. However, the equation that we put together doesn't realize that the acceleration is no longer minus 10 after the moment you come to a stop. Instead, the equation we've written down believes that the acceleration is negative 10 forever, so that after slowing down, passing by the deer, at t equals 2 seconds and velocity equals 10, you come to a stop at x equals 45, and then your negative acceleration continues, and so you back up and run that deer over one more time, maybe out of spite. That doesn't actually happen with your car, and so for that reason, we're going to reject the answer of t equals 4, and we're going to decide that the solution to this problem is the first of the two times when you're crossing the deer still traveling in the plus direction, so that t equals 2 seconds. Last part of the problem. Luckily, this is one smart deer. The deer runs to the side and needs to move a minimum of 1.2 meters to avoid being hit. What acceleration of the deer is necessary to just avoid the collision with your car? This falls into the category of problems known as definition of success. We need to take the information given in the problem and specify a specific condition that the deer's motion should follow. And once specified, that will lead us to an equation, a solution, and we're done. So let's make a quick diagram of what's going on. Here is your car in blue. It's moving to the right. The deer, that I'll draw as a simple oval, is standing waiting to be hit. In my experience, most deer stand in the road, stare you down, and hence the expression deer in the headlights. This deer, however, seems to be a little bit smarter, and so this deer is going to take off, trying to avoid the collision. Now, of course, if this deer were to move to the left, this wouldn't be a very smart move. That would be increasing the probability of the collision. If the deer were to move to the right, it's actually got to go a full 5 meters to get beyond where you stop, which is at 45. So the deer is smart enough that the deer will sidestep. Just to be clear with my notation, for this reason, I'm not going to refer to the x of the deer for this part of the motion. Instead, I'm going to refer to the deer's motion as being in the y direction. Now, what do we need to achieve? The deer needs to run to the side and move 1.2 meters. That means we're going to place a condition on the y of the deer related to 1.2 meters. However, this is an ill-formed condition. It is not a definition of success. It simply says the deer may reach 1.2 meters or may not, whenever. We need to be specific with this condition in order to fulfill the problem. Now, what we know is that the equations for the deer contain no variables whatsoever related to the car. There is one and only one variable that is found in both the equations for the deer and the equations for the car, and that variable is the time t. So what we require of our deer is that the deer should reach the location 1.2 meter at a particular time, and that time is the solution to the previous part of the problem, the time at which the car reaches the deer's location, and we found that that time was 2 seconds. This is the definition of success. If the deer's y location is 1.2 when t equals 2 seconds, the deer will have jumped out of the way of your car, save you a lot of money. To realize this condition, we need to invoke the equation that is implied by our formula. Our formula is a relationship between the y of the deer and time, and so immediately we turn to this formula. Y of the deer is y0 of the deer plus v0 of the deer times t plus 1/2 acceleration of the deer t squared. Let's plug in. We require that y of the deer be 1.2 meters. y0 of the deer is the initial y position of the deer. Although the deer is sitting at x equals 40, its y position is 0. The initial velocity of the deer is also 0, leaving us with 1/2 acceleration of the deer times the time squared, and the time we said should be 2 seconds. 2 squared is 4, over 2 is 2. Divide the 2 to the other side, and we have an acceleration of the deer of 0.6 meter per second squared, necessary to avoid being hit by the car.